with Stephen and Xanda and Ming and Hannah. And the high-level idea with this paper, we're at the intersection of two settings. And in one setting, you have a bunch of count data, and you want to fit Poisson Factorization with Bayesian Inference. Okay, so that's actually a pretty common setting. If you run topic modeling like LDA, you're in that setting. If you're doing a stochastic block model, you're probably in that setting, okay? But your data is sensitive, say it's like email data, okay? And so you want to make some sort of guarantee that this is not going to reveal anything too sensitive about the people involved. And specifically, you're in a setting where we want to noise the data ahead of time, okay, to ensure that privacy. And so at this intersection, there's a couple things that are tricky. One is, what's a good way of noising sparse, high-dimensional count data that doesn't destroy the utility of the data? And then how do you do Bayesian inference in these Poisson models if you only get to observe the noised version of the data, okay? So here's a scenario that motivates it. Imagine you have this research company, and there's a bunch of researchers, and they collaborate, okay? And the management decides that not enough researchers know about each other's work, and so the management's bright idea is that they're going to run a topic model on the internal emails of this company to see, what people are talking about and connect researchers that don't know about each other, okay? So a topic model is typically going to return two sets of parameters. One of them is going to say at a very high level, what are the topics that are being discussed in these emails, okay? And then the other set of parameters is going to say, these people are talking about these topics, okay? And so let's say that in principle, these researchers are okay with people knowing at a very high level the topics that they're talking about, but they want to make sure that this procedure doesn't reveal anything too specific about what's in their emails. And specifically, if you rerun this topic model, right, after removing a single email and you get slightly different latent structure, can you back out anything specific about that one email based on the fact that you ran the algorithm twice and it got slightly different parameters, okay? So you want to guarantee that you can't do that. Okay, so we're in differential privacy, and we've already defined this many times. The way, and I'm not going to go over that, the way that we're going to satisfy differential privacy falls into three different categories, roughly, okay? So one is that you can satisfy differential privacy by showing that an algorithm is inherently stochastic or noisy, okay? So if you run it twice and you get two different answers, that's attributable just to the fact that the algorithm is noisy. You can also noise the output, okay, same idea, or you can noise the data itself, okay? And this is what we're going to call local privacy, and this is nice in the sense that the individuals can noise their own data and then send it along, and they don't have to trust anybody to implement differential privacy correctly, but it might be a little bit harder, right? So these models typically represent a bottleneck, and if you add noise after the bottleneck, you may not have to add as much noise to make the same sort of privacy guarantee, okay? So there's challenges involved in local privacy, but this is the setting we're in. As a good Bayesian, you want not just a point estimate of the parameters, but you want to infer a posterior distribution, okay? So that's going to be your distribution that characterizes the uncertainty about what the values of your parameters are given what you know. It's almost always intractable, so you do Bayesian inference, and this is where you are going to approximate this with some distribution Q. And in machine learning, there's basically two main ways of doing this. One is variational inference, where you choose some Q from a set of functions that's easy to optimize. And the other one is MCMC, where Q is a set of samples drawn from the posterior, okay? This is what we're going to do, MCMC. And there's work in, let me tell you how to draw samples from an intractable posterior. So if you set up this Markov chain where you resample your parameters, so you sample the first set of parameters conditioned on your current sample of the last ones, and then vice versa. Typically, these complete conditionals, you can form them and you can sample from them, even though you can't form the full posterior. So if you run this Markov chain forever, then eventually it will be drawing samples from the exact posterior, okay? And in practice, you just run it for a while, and it works out. Okay, there's work in differentially private MCMC. So if your algorithm returns one sample of your parameters, which is going to be a terrible approximation, but if it returns one sample, then this has inherently privacy-preserving properties. You can also add noise to your samples, or you could perturb those complete conditionals, that transition kernel, okay? But so all of these approaches they're gonna condition on the actual true data, okay? So this is in the global privacy setting. When you're in local privacy, we have to consider this object. We're calling it the locally private posterior, and this is, it's the distribution of your parameters given what you observe, which is the noisy data, okay? And you also get to condition on your model assumptions for the sensitive private data and your knowledge about the randomized response method, which is this thing that you're using to take in private sensitive data and output noised privatized data, okay? So the locally private posterior, so that's what we want to fit, but let's be honest, there is an alternate option, which is we can just run our non-private inference code and pretend like the noisy data that we have is the real data, right? That's easy, but it's naive, okay? So let's look at the object that we actually want to get to. This is going to treat the real underlying data y as a latent variable, then marginalizing it out, right? That's what that posterior is. And so in the context of MCMC, we can form this posterior by sampling values of the underlying data as if it were a latent variable, right? So we can set up this Markov chain. These two steps are exactly the same as the ones that I showed you before. So if you have an implementation of non-private MCMC, you can just call this code conditioned on your current sample of the underlying data, and the only thing you have to figure out is how to sample values of the underlying data from its complete conditional. So depending on your assumptions about the model for your underlying data M and your randomized response, this may be easier or harder, right? So what we show in this paper is that if you choose your model to be Poisson Factorization, which is natural and widely used for counts, and you choose a certain randomized response mechanism I'll show you in a sec, then they work together nicely and we can sample from this efficiently. All right. So let's get to topic modeling. So topic modeling is going to begin with this email corpus, and it's going to represent it as a count matrix. V by D count matrix. You have the total number of words in your vocabulary by the number of emails or documents. And a certain email or document is a row in that. And so it's going to be the length of the number of words in your vocabulary. So this document maybe mentions, these two words multiple times, but in general, these documents, most emails don't mention most words. They're going to be very sparse. They're going to be very high dimensional, okay? So keep that in your mind. Most topic models, LDA included, it's a form of Poisson factorization. So the assumption is that all of your counts, so the count of word type V and document D, it's a Poisson random variable with some latent rate. And that rate is a function, it's a linear function of your shared model parameters. So in this case, the rate of word V in document D, it's equal to, you sum over your latent topics, multiply how much document D uses topic K by how much topic K uses word type V, okay? And this setup is going to generalize lots of existing models. Topic models, stochastic block models, recommender systems, a lot of these are examples of Poisson matrix factorization, but more generally, if you have a collection of counts that you organize in a tensor or whatever, so long as you assume that they're conditionally independent Poisson random variables, the stuff that we have in this paper applies, okay? So let's talk about the randomized response method. So typically, the sort of standard choices in the differential privacy toolbox are Gaussian or Laplace noise. You add them to all of the data points that you have, but that's sort of unnatural for counts. If I add a bunch of Laplace noise to counts, I have a real valued data set, right? And I lose the discrete nature. There is this existing mechanism called the geometric mechanism. So in this case, I'm going to add, for every count in my data set, I'm going to add a two-sided geometric random variable to each count. And this is an integer valued random variable. So if I have a count matrix and I do this, I'm going to get back an integer matrix. Okay, so here I'm being very explicit. So y tilde is the noise data. We're subscripting it with plus minus to mean it could be negative, right? You now have integers. It could be negative, okay? All right, what is the kind of privacy guarantee that this gives you? This is local privacy. Similar to differential privacy here, the idea is that a randomized response method, if it takes in y and it takes in y prime, so two different documents, and here this circle is the space of possible documents, okay? So if I take in y and map it to some noisy other document, and I take in y prime and map it to some noisy other document, I want it to be very unlikely that if I only see those privatized versions, I'll be able to tell that they actually came from different places, okay? So that probability is parameterized by epsilon. This is the form of the privacy guarantee the geometric mechanism was originally given for. It's sort of standard local privacy. It depends somewhat silently on this assumption of the sensitivity, which says that two documents will never be more than some distance, so n max apart, okay, in edit distance, basically. And n max is going to determine how much noise we need to add in order to achieve a certain epsilon privacy. In practice, this is difficult, right? To make sure that two documents, which are very high dimensional count vectors, are rendered basically indistinguishable after noise, we're going to have to add a ton of noise and lose the utility in the data, right? So we're going to use a generalization of this idea, which is inspired by this paper. We're calling it limited precision local privacy. And here, you're going to add a certain amount of noise to the data, and it's up to you how you want to interpret that. So if you choose N1 to be your sensitivity, then what you're saying is that I'm going to render Y, my document. I'm going to have privacy within a small neighborhood around Y, so around similar documents. I'm going to have a good level of privacy, but I'm not going to, for example, have a very good level of privacy if another document Y double prime is very different from Y, right? And this is sort of natural. Maybe I don't care that you know I'm writing emails about the Mueller report, but I don't want you to know that I cursed a couple times, right, with a couple words, right? I only care that the document I'm giving you, you can't tell up to a certain small number of words if they were really in it or not. So we show in the paper that the geometric mechanism, it's a mechanism for this type of limited precision local privacy. If you add two-side geometric noise with this epsilon to your count data, then it has this relationship to epsilon and n, and it's up to you how you want to interpret that level of noise. Okay, so to recap, we have our model. It's Poisson matrix factorization. We have our randomized response mechanism. It is the geometric mechanism. And now the challenge is, can we sample values of the underlying data given those two assumptions, okay? So I'm going to sketch the solution. It's based on two theorems, two results. The first is that a two-sided geometric random variable, we could generate it like this. We can also generate it by first sampling two exponentials and then sampling a scalum random variable with those two parameters. Okay, the scalum is the marginal distribution of the difference of two Poissons. Okay? The consequence of this is that we can assume that the noise data that we observe, we can assume that it is scalum distributed. Okay? Second theorem relates the scalum distribution to a different distribution, and it looks like this. So if I have two independent Poisson random variables, G plus G minus, and I define their difference and I define their minimum as deterministic functions, then the joint distribution of tau and m, if I marginalize out my Poissons, is I can represent it as I first draw tau from a scalum, and then m is a Bessel random variable conditioned on tau. So the Bessel is this discrete distribution. It's like an underdispersed Poisson, okay? And the consequence of this is that if we begin by assuming that the noise data that we observe is a bunch of scalum random variables, then by sampling an auxiliary Bessel random variable, we can recover the latent Poissons that allow us to facilitate inference of the parameters. Okay, so without too many details, this is basically what our sampling procedure looks like. You sample a Bessel for every integer in your noise data set, then you sample a binomial, and you recover a sample of your data. And you can do both of these efficiently. So the Bessel is underdispersed. There's fast rejection samplers in the literature, and we have code online to do it. Okay, so in the paper, we consider two case studies here. So one is topic modeling of documents, and the other one is community detection in social networks. Those are both examples of Poisson matrix factorization. And for both of them, we're going to think about synthetic data, where it's drawn from Poisson, and then real data from the Enron corpus, okay? And in both cases, we're going to compare this proposed private approach to the naive method that doesn't treat the underlying data as a latent variable and just fixes the noise data to its values. The naive method has to first truncate negative values to 0, okay? And then the non-private method, so running Poisson factorization on the raw data that has not been privatized. And so here's some results from real data on the NRON. So this is error, so higher is worse, and the takeaway is don't be naive. The error for the private approach is very, very close to the non-private approach here. And what's interesting is that if you also measure the coherence of the topics learned, so this is a measure of interpretability or topic quality, the private approach actually gets infers more coherent topics than the non-private approach and the naive approach. Okay. In community detection, here is some synthetic data. So on the top row, we have, in the top left is the true data that we generate from Poisson factorization. And then each column, we're going to noise that by a little bit more each time. The second row is if you take the naive method and you fit it to each one of these noise matrices and then ask it to reconstruct the underlying counts, that's its reconstruction. And the bottom row is us, okay? And so even for high levels of noise, the method that treats the underlying data as a latent variable is able to reconstruct that block structure almost as well as the non-private approach. So this is for synthetic data where there's no model mismatch. On real data, on Enron data, we find that here, again, higher is worse. This is error. The private method is actually getting consistently lower error than even the non-private Poisson factorization on the raw data. And this is at reconstructing the data that the non-private method fits to, okay? So what's going on here? Well, there's a lot of previous results on how privacy can act as a regularizer, right? And specifically, this is more of an indictment of Poisson factorization when you have model mismatch. So we're not finding these results from synthetic data, but when you fit to real data that maybe doesn't exactly match the Poisson assumption, then it may actually be better to add noise to your data and run MCMC that is not naive about that noise. You may actually be doing better than running a mismatched model that assumes the data is Poisson when it's actually not. Okay. Thanks.
All right, so we have a few minutes for questions.
It's refreshing to see using a real-world data set rather than synthetic data set. With the Enron email corpus, with regard to topic modeling, are the emails pre-processed where the email thread actually drops all of the CC threads below and simply the original email is used, or is the thread actually included? And the reason I ask is when you topic model with your documents by words, then that obviously changes the matrix.
Yeah, we only use the original emails. And so for the two, we do topic modeling where we take every email in its original form, turn it into documents by words, and then there's the community detection where we're just looking at who is sending emails to whom in a adjacency matrix where a count is the amount of emails sent between two actors.
Other questions? I have a quick question. Did you look at what would happen if, for the naive model, instead of truncating, you found the largest negative and estimated and shifted back? Would that work, or so is there something in the truncation that maybe is losing information?
So in the naive method, find the most negative value and then treat it, and then
I'm trying to figure out a way to make it all positive so you can apply a generic Poisson factorization.
That's not just taking the negative values and putting them to zero?
Yes.
That's something different than that?
Yes. So shifting essentially instead of.
Oh, I see.
Zeroing.
Oh, no. You mean adding I see.
So I'm mostly thinking of the information loss by throwing that away. And do you think that would, so if you haven't done it, do you think that might improve?
Actually the naive method it's pretty good. So the original geometric mechanism paper, that's what it recommended. It's called the truncated geometric mechanism. And it's actually, if you think about it, like, and a lot of times your counts, you have these, ones, twos, and those counts that are kind of noisy, they oftentimes get just mapped to negative values after you add noise. and then after truncating, they become 0, and it's actually a pretty good. It makes it so that the naive method is focusing on really the most salient patterns without getting without modeling all the little stuff. I don't know about a different, we didn't think about like truncating out, but we did think about a hybrid approach where you are treating only some of the counts as if they came from the noise. So you sort of truncate up all the negatives and fix the zeros, and then only for the positive values do you do this latent variable approach. And that's better for computational reasons.
Interesting. Other questions?
I have a really high-level question here. How is this different from obfuscation, essentially?
I don't know what that is.
So what does an attacker need to know to reverse this?
I see what you're saying. Okay, so in the local privacy domain, once you add the noise to the data, if you only see the private responses, you can do anything you want to that. You'll never reverse that privacy guarantee. So if you're in that local privacy domain, you should be squeezing as much information as you can out of that noise data, right? You should be trying to reverse to, infer the tightest posterior distribution over the true values of the underlying data as you can, because you can't do anything to reverse that privacy guarantee. And so anything you do that isn't, squeezing as much information as you can is just giving away privacy for free that you didn't, quantify.
Okay. I'm not sure I fully understand, but if you have any spare time to talk afterwards,
sure.
That'd be great.
Okay, with that, I'll thank the speaker.